infinite amount of energy to accelerate any material particle having a non-zero rest mass up to the speed of light. The only reason photons can go at the speed of light is that they have no rest mass. If you were to put a photon on a table, it would cease to exist. So, relativity prevents particles with non-zero mass from reaching the speed of light. But it does not forbid superluminal expansion. And indeed, during inflation, you have superluminal expansion in spades. Here's what's going on. Suppose I have two ping pong balls, these are galaxies, that are separated from each other by more than 300,000 kilometers, okay, just by some very big distance, okay? And now I tell space to expand in size. Let's say I synchronize all the clocks and I just tell them that at noon they're going to each double in size, so each centimeter is going to turn into 2, okay? Well, two galaxies that were originally separated by more than 300,000 kilometers will now, after 1 second, be more than 600,000 kilometers apart. Thus, they will have moved away from each other by more than 300,000 kilometers in 1 second. That's the speed of light, okay? So they will have moved from each other faster than the speed of light. But that's only because of the cumulative effect of every centimeter, no, millimeter, nanometer, doubling in size, okay? It's a very local effect which globally turns into a very big expansion speed. But you can't use that stretching of space to send any particle or any information from one ping pong ball to the other. Indeed, the very fact that space is expanding faster than the speed of light is what prevents any signal, any particle, any material particle from ever getting from this ping pong ball to that one. Because it covers some space, but the remaining space is expanding faster than the speed of light, so that particle can never get there. But during inflation, the universe doubles in size, it goes from like anything you want, a proton, to way bigger than you need with 100 doubling times. You try folding a newspaper, okay? You can do it maybe 7 times, okay, if you're really good at it. 100 doublings is just enormous. 1,000 doublings is almost beyond comprehension, right? 1,000 doublings, that's 2 to the 1,000th power. That's roughly 2 to the 3rd to the 300th power, very roughly, okay? 2 to the 3rd is roughly 10, so that's 10 to the 300th power. Do you know what kind of a number 10 to the 300th is? Do you know how many particles there are within our observable universe? Photons, protons, you name it, put them all in the bin. How many particles are there? 10 to the 80th. So numbers like 10 to the 100th and 10 to the 300th are so beyond comprehension that you get these truly gargantuan universes. Universes, like I said, that can easily be so much bigger than the part we observe that the part we observe is like a proton in the whole thing. So the universe goes whoosh. That happened in a split second. Then the dark energy of back then, the inflaton, turned off. For reasons we don't understand. It decayed into something that's gravitationally attractive. Okay, so the acceleration of the apple was the inflation, and then I let go of the apple. That's when inflation turned off, and the stuff of which inflation was made, which is you and I and everyone else, that became gravitationally attractive. Okay, so from that point on, the universe started decelerating like this apple, and that did that for 9 billion years, and then 5 billion years ago, this weird dark energy took over for reasons we don't yet understand, okay? But right after inflation, the universe was gigantic. Stars, light bulbs, only started forming some 200 million years after the Big Bang. Okay? And the 380,000 that you were referring to, that's where the cosmic microwave background radiation comes from. That's where the universe just consisted of little tiny density fluctuations of a few parts per 100,000, okay? But stars had not yet formed, okay? But even if stars had formed at that time, at 380,000 years, instead of 200 million, they're forming like light bulbs in a pre-expanded universe, kind of like a pre-baked, loaf of bread or a pre-baked pizza. You can bring them home and bake it the rest of the way. So here's this gigantic universe, and then stars start forming. Okay, once a star forms, it starts sending light out. How far will the light get in 1 year? Well, out to a sphere of radius 1 light year. And at this point, let's ignore the the additional expansion because it's almost irrelevant. Okay? So in 1 year, the light gets out to 1 light year. Stars within 1 year, or creatures within 1 light year of that star will see it come into existence, you know. Creatures that are 10 light years from it will not yet see it. Okay, right? But in 10 years, that light will reach those guys, and in 100 years, it'll reach the others. So the observable universe keeps growing with time. And we're not limited in terms of the size of the universe by the amount of time it has existed and the speed of light, because it grew superluminally by many, 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 many factors during this inflationary stage. And even though we're not inflating right now, we're only accelerating, and actually even in a decelerating universe, parts that are sufficiently far away from each other are in fact still moving away from each other faster than the speed of light, because every little bit of space expanded, and the more space you have, the greater will be the total amount of expansion. But that's a very good question, which is why I tried to answer it at length, because it's the reasonable deduction. What you said was not unreasonable, and the explanation is actually quite subtle. Yeah. Other questions?
No, I'm afraid not.
Sorry.
Maybe at the podium, if you're willing,
I didn't know
Alex.
what time it was in my frame of reference.
I want my frame's time to last longer, but we'll give Professor Filippenko, I hope, a mighty round of applause in just a minute. Another mighty round of applause in just a minute. I hope you'll indulge me. Let me take care of just a little business here. There are some people that deserve some thank yous for making this event.